Well, hello everyone and welcome to our next video in the Chem 2100 series, Organic Chemistry 1. In this video we'll do some material out of chapter 1 and 2 out of the Klein textbook, which is really material that we think you know from the general chemistry courses that you took to kind of join us in this particular course here. So there'll be a few important topics that we think we'll kind of put them in a little bit of an order where we think they're important for us to know as organic chemists in this particular course, and focus on some of the aspects of general chemistry curriculum that we think are important for people in our course to be able to pay attention to, and we're going to lean on these concepts really quite heavily as we go throughout the term. So let's take a look at some of those review topics, or again, things we think you know from first year chemistry. Of course, we think you know the periodic table, and as we hinted in a different video, that periodic table really shrinks down for us as organic chemists. We focus on the first row elements, that is boron, carbon, nitrogen, oxygen, and fluorine, some of the halogens, and a few other, some of the earth and rare earth metal ions. The transition metal elements appear in this mysterious center block, and we don't get the opportunity to see them very often in this particular course. Now again, a quick review of topics that we talk about in general chemistry. We talk about building up those electrons of that first row of the periodic table. We start ultimately from sodium, but boron, carbon, nitrogen, oxygen, fluorine, up to neon, those inert elements that don't react very much, kind of build this up here. So I don't want to go over this in too much depth. This is something we spend a lot of time on in general chemistry. But one of the things that we do spend some time on, or focus on here, at least in organic chemistry, is how those electronic configurations and how we use them to understand structure and bonding. So for example, if you look focusing on the electronic configuration of carbon, you see there's 2 electrons in the 1s shell, 2 electrons in the 2s orbital, and 2 electrons in the 2p, each with a single unpaired electron. So based on that electronic configuration, our prediction would be that carbon can only make 2 covalent bonds. And of course, a covalent bond is an equal sharing of 2 electrons between 2 atoms of whatever those 2 atoms are. And so we'd predict, because there's only 2 unpaired electrons in the 2p orbital, we'd predict to make only 2 covalent bonds to a carbon atom. However, that's not consistent with our observations on carbon. Our observations that carbon can make 4 equivalent carbon-hydrogen bonds. We won't talk too much about how we know they're equivalent, but we can do experiments that show that. And so that observation doesn't match with our prediction, so we have to come up with an explanation for why we observe that. And our explanation is hybridized orbitals. So what we say is that we hybridize the 2s orbital with the 3 2p orbitals and generate 4 new degenerate or equal in energy orbitals that we call sp3. That is this hybrid mix of an s and a p, 3p orbitals, and all now of equal energy, somewhere in between the 2p and the 2s orbitals. Now each one of those orbitals can hold a single unpaired electron, and then we can use those to match up to make those 4 equivalent carbon-hydrogen bonds that we observe in methane. And so that's our explanation for those observations of 4 bonds instead of our predicted 2. And we can match those unpaired electrons in the sp3 orbitals with a single electron from each one of the hydrogen atoms that we use to make those 4 bonds, equivalent lengths. And then we get bond angles of 109.5 degrees. And again, those bond angles are predicted by that so-called valence shell electron pair repulsion theory, or VSEPR theory, that explains where we get those bond angles from. And we see this as we go up into the higher hydrocarbons, and we'll spend some more time on that next week. Those higher hydrocarbons like ethane, we still use that model of these hybridized sp3 orbitals to explain the observed bonding in those elements and in those hydrocarbons as well. And so this concept of an sp3 hybrid orbital and how we get this tetrahedral shape as we describe it in methane and the other sp3 hybridized carbon atoms that participate in bonding have this tetrahedral shape. That's all things that we think are covered quite extensively in general chemistry. And so beyond this discussion, we don't want to go back to them too much, except to say that we will lean on these concepts quite heavily throughout the entire term. And so I think it's things that we hope that you're really quite familiar with. Now, out of chapter 1 of our textbook, there's a couple of other things that we think out of general chemistry that are really important for us to use, concepts that we lean on in organic chemistry. Now, electronegativity is one of those, and so I don't want to dwell on this too much. It's something we think or hope was covered in general chemistry quite extensively. But in general, in the periodic table, we see as we go up or across to the right on the periodic table towards the halogens, we get increasing electronegativity. Fluorine is the most electronegative element in our periodic table, and it goes down from there. And there's numbers associated with those electronegativities of each element, and what they allow us to predict are trends in bonding, in those covalent bonds that we would expect to observe. Small electronegativity differences, less than roughly about 0.5 of these electronegativity units, means a non-polar covalent bond. Polar covalent bonds in a range from that 0.5 up to about 1.7, and anything with a much larger electronegativity difference we usually describe as ionic bonding, although at each one of those boundaries there's some covalent bonds that are a bit blurry, and we'll get the chance at the very end of the course to see a few of those types of bonds as well. Again, these are concepts we think are well developed in general chemistry, and I don't want to lean on it too much at this point in time, except to say we use that idea of electronegativity to rationalize an awful lot of the observations about how bonds behave in organic molecules. And one of the ways we see those rationalizations appear is in our analysis of intermolecular forces. So here, for example, we're talking about hydrocarbons. And again, when we start chapter 4, we'll look at these in a bit more depth. But one of the things that we observe is that hydrocarbons have relatively low boiling points, and they are all non-polar bonds. The electronegativity difference between carbon and hydrogen bonds is 0.4 on that electronegativity scale. Those are considered non-polar bonds, but even non-polar molecules can generate intermolecular forces like London dispersion, or we sometimes call them van der Waals or instantaneous dipole forces. And the figure at the bottom gives us a little bit of an idea of what we mean about those instantaneous dipole. At any instant, there might be a small dipole build up in one molecule, and that induces a dipole in the next molecule over. And if you stack enough of those together, you get enough interactions that the molecules can interact with each other in an intermolecular way, so much so to the point where something like hexane has a boiling point where it's a liquid quite easily at room temperature. And again, our understanding or our model for these intermolecular forces is also a consequence of our understanding of electronegativity of the individual atoms. So again, concepts that we'll use quite often throughout the term and in subsequent courses when we discuss this kind of thing. Slightly stronger intermolecular forces are dipole-dipole interactions, and these happen when we have bonds that have a slightly larger electronegativity difference. So now we're looking at the difference between a carbon and an oxygen here, for example, as we go from isobutylene, again a relatively non-polar molecule. It's got a carbon-carbon double bond, but we'll talk about those in a couple of days in some more detail about the bonding that takes place there, if you haven't heard that. Very low melting point, it's a gas at room temperature. Acetone, now we've got a carbon-oxygen in that, a bond in there, double bond in this case, and we'll talk some more detail about those types of bonds later. The main thing to focus on is the electronegativity difference between the carbon and the oxygen, 2.5 versus 3.5. That's greater than 0.5, it's a difference of 1. We would consider that a polar bond, and that we see that reflected in the intermolecular forces here, where that polar bond sets up what we call a dipole in that acetone molecule. Those dipoles can line up. They're permanent dipoles. They're a constant feature of that molecule. And they can line up and raise the boiling point of acetone to the point where it's a liquid at room temperature, 56-degree boiling point. And then another intermolecular force that we pay an awful lot of attention to in organic chemistry, because it explains a lot of things that we observe in this particular course. And if you're taking Biochem 1, it explains an awful lot of the things you're going to learn about in that particular course as well. And that's the hydrogen bonding. So it's not strictly related to dipoles or electronegativity, but it is related to the fact that oxygen-hydrogen bonds are really quite unique in the way they interact with each other. And this also applies to nitrogen-hydrogen bonds and bonds between a hydrogen and a fluorine. Now, we don't see many HF bonds in this course, but we do see a lot of oxygen-hydrogen bonds and a lot of nitrogen-hydrogen bonds in this course. They turn out to be really quite important. And so what we observe here, for example, is the boiling point difference between methoxymethane. Again, simply a dipole there between the oxygen and carbon, boiling point of -23. Ethanol, where we've just simply moved one of the carbon atoms around a little bit, has that oxygen-hydrogen bond, has a boiling point well above room temperature, just about 80 degrees Celsius, and it's a consequence of this hydrogen bond. Again, this is a concept we think is well developed in general chemistry. It's discussed in a lot of detail in chapter 1, but it's something that we think is very critically important for organic chemistry. So I just want to make sure that if you kind of haven't looked at it for a while, it's something you may want to take a little bit of a look at. And so for me, that's really the core of what I'd like to focus on for chapter 1 material. And for chapter 2 material, what I'd like to take a focus on a little bit is just to make sure that we see some of the material from chapter 2 that I think is kind of important, and we'll develop this a little bit more in Friday's lecture slot as well. And so one of these is molecular representations. And in that chapter, it talks a little bit about how we go from a Lewis structure, which is what we build up in general chemistry, to these partially condensed structures, and then ultimately molecular formulas. And there is a separate video that we'll post that I'll refer you to on wedge and dash formula and line drawings in a little bit more detail about how we represent chemical structures in organic chemistry. So these types of representations of molecules are just different ways of representing either the chemical formula or molecular formula or some partial structural information about the molecule that we're looking at. I just want us to be familiar with it at this stage, get a look at it, and we'll spend a bit more time in that other video, like I said, focusing on how we like to think about these things in organic chemistry. But those line drawings lead us into these sort of functional groups. This is a big table in chapter 2, and I just want to point it out almost in passing at this stage to say we're going to spend an awful lot more time looking at these functional groups later in the course, probably in a few weeks after we finish chapter 5 material, and kind of look at these in more in-depth. But understanding what these figures on this page represent is a consequence of understanding those molecular representations. So I would say take a look at that section in that part of chapter 2 and pay a bit of attention to what's being talked about there. Now, one other thing I want to touch on as we kind of wrap up this particular review section, this review video, is as a consequence of Lewis structures, one of the things we talk a lot about is understanding formal charge. And so what I want to say is that identifying formal charge is an essential skill for organic chemistry. And so here we've got just a little bit about how to understand formal charge on oxygen atoms, whether it has the right number of hydrogens with 2 lone pairs of electrons, or the right number of 2 covalent bonds and 2 lone pairs is no charge, 1 bond and 3 lone pairs is a negative charge, or 3 bonds and 1 lone pair is a positive charge. Not so much to focus on the specifics, but just understanding how do we calculate formal charge, and just a bit of a recall of some of those skills, being able to learn how we do that kind of stuff, just so that we can do it almost at a glance and remember the rules for calculating formal charge. And just as a wrap up of this then, related to Lewis structures and the concepts of formal charge and all these things we've been talking about, I want to spend just a minute or two here as we end this on another concept that comes out of our study of Lewis structures and basic structure and bonding in general chemistry, and that's the concept of resonance. So this is a core central concept to organic chemistry. We'll spend a bit of time on the lecture at the Friday on talking about this material in some more depth. But I want to pull an example out of general chemistry, one that we often look at, which is the carbonate anion. So CO3 with a -2 formal charge on the ion as a whole. Again, I won't go through the exercise of how to draw this particular Lewis structure, just remembering that the rules are we want to fill everybody's octets and minimize formal charges. And if you've done that step correctly, this is the Lewis structure that you should come up with in that instance. What I want to focus on a little bit more detail is how we move these 2 negative charges around this molecule in resonance, and what that means overall for our understanding of how this ion behaves. So let's focus on this in some more detail here. And what we're doing with this particular exercise here is we're moving electrons around. So this isn't a chemical reaction. We're not changing any of those so-called sigma bonds or those single bonds between the carbon and the oxygen. We're simply looking at the double bonds between the carbon and oxygen, and those electrons that are involved in those lone pairs that make up the formal charge on each of those 2 oxygens that carry it. But if we look at the ion carefully enough, what we can recognize or remember, hopefully from general chemistry, is that we can move that negative charge around. So that first set of arrows that I'm drawing there, I'm moving the negative charge from one of those oxygens, and localizing it between the oxygen and the carbon atom. But in order to do that, I can't violate oxygen's octet. It's already got 8 electrons around it, so I have to make some space for those incoming electrons. And I can do that by pushing them up onto the oxygen atom in the top of the way I've drawn it, this molecule. Now I'm separating these two resonance structures by the so-called double-headed arrow. This doesn't imply a chemical reaction. That double-headed arrow is just something that we use as chemists to remind ourselves that we're looking at resonance structures. So that double-headed arrow, we'll see that an awful lot. And then the next structure I can draw is where I can use, in that center structure, I can use a pair of arrows to show that I'm moving the electrons from that single oxygen with the negative charge. Now again, making a new carbon-oxygen double bond and opening up the octet or moving electrons away from the carbon atom to go on, localizing them onto the other oxygen atom to give it a full formal negative charge. And again, I'm using these what we call curved arrows, the ones I've highlighted in red. They're an arrow where we're showing that we're moving electrons. And in general, we move electrons from somewhere to somewhere else, and we use those arrows to represent that. So I'm moving electrons from an oxygen atom to a newly formed carbon-oxygen double bond, and I'm moving electrons from that carbon-oxygen double bond out on top of that oxygen atom. And again, we're kind of expecting that some of these rules were covered in some depth in general chemistry, but we'll get an opportunity to go through them some more depth together as well. So now, what these structures are meant to imply is not that the electrons are actually moving in the molecule itself. This is an exercise that we as chemists do on a piece of paper to try and come up with an explanation for what we observe. And what we actually observe in these kinds of ions is the hybrid of all of these kinds of on-paper constructs that we've come up with in a concept called the resonance hybrid. And really what we come up with this resonance hybrid is we introduce the idea of delocalized electrons. That is, those two negative charges that exist on carbonate anion are delocalized amongst all 3 of those oxygen atoms. And in fact, each of those 3 oxygen atoms carries effectively a 2/3 of that negative charge. 2 negative charges delocalized over 3 atoms. And those electrons that we were moving around on our piece of paper with those red arrows actually can be considered to be delocalized amongst all 3 of those oxygen atoms. And so this, for us as organic chemists, turns out to be an exceptionally powerful concept, as it's going to help us explain an awful lot of what we observe in our organic molecules when we start looking at trying to be able to explain reactions or look at things that we're talking about in these particular molecules. So let's take a look at one organic type example before we wrap this up. We can apply this concept to organic molecules, and here we've got an oxygen with a carbon and a double bond. And again, if you're not familiar with these molecular representations and what we're showing here, you'll get an opportunity to look at it. And I would say take a little bit more careful look in the chapter at what we're actually representing here. We haven't explicitly drawn hydrogen atoms. And we talk about this a bit more in the video where we go from wedge and dash formula to line drawings. We've got a carbon-oxygen double bond, and we've got an oxygen with a full formal negative charge. And as we saw in carbonate, we can push those electrons in those double bonds around like we did with the carbon-oxygen double bond. So what does that look like in this particular instance if we do this? So again, the red arrows show that we can take a pair of electrons from the oxygen and push them in to make a new carbon-oxygen double bond, but we can't violate that carbon's octet. So we have to push 2 electrons from that carbon atom out onto the other carbon atom at the end. Now that doesn't violate the octet. We've still got a lone pair of electrons, 2 carbon-hydrogen bonds, and a carbon-carbon bond. And again, if you're not following that, take a look in some detail where that's reviewed in chapter 2. But that also generates a full formal negative charge on that carbon atom. And so where we put that new negative charge. We haven't violated any of the rules of Lewis structure bonding. All of the electrons have, or all the carbon atoms have, or all the atoms in general have 8 electrons around them. We haven't violated the octet rule. Maybe a little bit about the charges, and maybe we're kind of wondering about how those charges look. We could maybe think that there's a delocalization of those 2 charges between the oxygen and the carbon. And so we could think about maybe this is the hybrid structure where those charges are delocalized. But one of the other concepts that we focus on when we're drawing these resonance structures is the idea of that electronegativity of those relative elements and how much that influences where those electrons would prefer to reside. And just if we remember the electronegativity values, we know that oxygen is far more electronegative than carbon, 3.5 versus 2.5. And that's a measure of how much that atom likes to stabilize or hold a negative charge and hold on to electrons. So one of the ways to think about this is that that would make this structure where that negative charge on the oxygen is what we call more significant. So in other words, unlike the carbonate ion, where if you look back to that, all three structures we drew had negative charges on oxygens, here we're being asked to make a choice between an oxygen and a carbon. Which one of these is more significant? They're both bona fide resonance contributors, but which one's more significant? Well, it'd be the one where the negative charge resides more directly on the more electronegative element. And so now we can start thinking about the resonance hybrid in this way, where we start thinking about the relative size of those partial charges and what influence might that delocalization have on that, on the electronegativity have on that delocalization. And so this idea of drawing resonances, trying to assess the most significant resonance contributor, and a little bit of how we picture those resonance hybrids are all concepts that we're going to be able to use to rationalize an awful lot of the organic reactions that we start talking about and the way molecules behave under certain circumstances. So for us, I think as in organic chemistry, these are core concepts that we really want you to be able to review. And so those are the major topics from chapter 1 and 2 that I think we should review. Honestly, if you're watching this video and by the end of it you're skipping through it, you're mildly bored and you think to yourself, man, I feel really good about these topics, I think you're going to be in good shape for the course coming up. If you had no idea what I was talking about, much of this went over your head and you're very confused about these concepts of resonance, structure, bonding, electronegativity, I'd say you've got a little bit of work to do reviewing chapter 1 and 2 and maybe even digging out your general chemistry textbook and having another look at some of the concepts that are in there. But other than that, I'll leave these concepts for now. I haven't talked about chapter 3, but we'll come back to chapter 3 and the ideas of acids and bases a little bit later in the course. After we get through chapter 5, we'll talk about those concepts that we pull out of chapter 3 that we think are crucial for organic chemistry, explain them in a little bit more depth, and kind of the things that we think are important out of that chapter. That doesn't mean you can't read that chapter, and I would suggest going through it because there's a lot of concepts in there that we think are core for organic chemistry. But for now, I'm going to leave the review there at this stage, and we'll just start next week on some chapter 4 material. So read ahead some of that chapter 4 material, but for now, I'll leave the recording here and the video here, and we'll see you all in the lecture.